Yeah, Grigory, you can go ahead.
Hello, everyone. Thank you for having me. It was a pleasure to give the first talk in this series. Um, I'll be talking about verification, a little bit about synthesis, but mainly synthesis of certain things. And the main ingredient in all these approaches is constraint one clause. So I'll tell what it is actually in the introduction. Don't worry if you don't understand or your first time you hear about constraint one clauses. It's totally fine. Please, I really like to receive questions as I go. So I able to see the chat actually, so you can type questions in the chat and I will read them and I'll answer them or interrupt me, well, if you wish. So I really like having discussion as basically one of the goals of this seminar. So what I'm doing mainly is automated reasoning about software. Software is the main motivating factor, and reasoning in terms of verification, synthesis, and any other type of useful things that we can know, would like to know about software and do it automatically. So I'm definitely not the first one, and there's a rich line of research preceding the things that I'm doing. Well, you definitely recognize pretty much all of this picked portraits beginning from Alan Turing, ending with Tony Hoare, Trick Kuzo, Ed Clark, and Zifakis Emerson, who invented model checking. What is if you're new to verification, this is roughly can be described as logic-based approaches where we take a program that we want to verify and generate a so-called model, or it can be often represented as logic formulas. So this logic formula encodes all behaviors of this program that we want to verify, as well as the desired specification, something that we really want to happen in something that we really want to hold independently on inputs and outputs of that can be observed. For instance, program never writes outside of allocated memory. So the tools that we build that are essentially the outcomes in this automated reasoning projects, they are basically they automatically construct these formulas and they automatically analyze them. So they essentially look at programs as formulas. And we also use state-of-the-art decision procedures to reason about these formulas. And all interesting properties that we can derive from formulas, they essentially map to important properties about programs that we want to find. So this line of research is by itself not new, and similar methods are applied in physics, for instance, 17th, 19th centuries, where, for instance, physicists wanted to derive properties about physical reality, and they used math as the main vehicle in order to, derive all these important laws. And they did some kind of abstraction refinement, because while they had a hypothesis, they built a model, they applied math, and they, if all the properties that were discovered using mathematics, that were validated on real scenario, and if it failed, they had to go and refine. Similar things we actually do in logic-based verification, abstraction and refinement. So I hope that everyone at least heard about this usual paradigm that many of us use in our research. So what's automated reasoning today? And that's definitely a hard question because we have many subdivisions in this discipline, but a lot of people are using SMT solvers. Well, if you have not heard about SMT solvers, I'll have a slide for you. But right now you can think about SMT solver as about a tool that take a formula as input and solved it somehow. And these days, SMT solvers are standalone tools that don't really need to know anything about software, and they take formulas as input, and they can really scale to pretty large formulas that represent pretty large software coming from industrial applications. Constraint horn clauses, the main topic of this talk, is just one layer on top of SMT. So you can think about that as one particular special case of SMT. And they serve as symbolic representations of programs with complex control flow, with functions, with loops, with combination of functions and loops, and so on. They can take safety specification called assertions. They may take some liveness specifications as well, make life more hard, but still possible. And verification can be viewed as translation to CHC and solving of CHC. And we see many good examples, such as C-horn plus spacer, which is a tool chain for verification of C programs, J-horn plus Eldarica, similar thing for Java, Rust horn for hoist, well, as the name suggests, it's the tool chain for Rust, and many others. More importantly, these ingredients are interchangeable. It doesn't mean that C-horn only works with spacer and J-horn only with Eldarica. You can actually swap things, and C-horn will work with Eldarica and spacer, and J-horn will work with spacer. This is because of modularity of this approach. There's one guy responsible for translation of programs into CHC level, and another guy is responsible for taking that CHC representation and solving that. So what I'm doing, something that can be called guess and check invariant generation. Don't think it's simple. Well, it sounds simple. In fact, there are many corner cases, many bottlenecks to make it actually working. But essentially, it's an iterative construction of solutions of CHCs using SMT solvers. I'll tell about that. Other techniques are, of course, also based on some simple ideas, but a lot of them work because of the integration of different techniques into the same tools. For instance, property directory reachability, some new things with machine learning and syntax guided methods. Okay, so let's go to the actual tool. So this is the very introductory slide for those of you who forgot what is Boolean satisfiability. Very briefly, because everything here is based on Boolean expressions, Boolean connectives, things like Boolean conjunction, Boolean disjunction, negation, and Boolean variables as well. So the task of Boolean satisfiability is figure out if there's an assignment to true and false for all these variables that make the entire Boolean expression true. And the simple examples with real Boolean variables x, y, z, and w. So this is the formula is built with Boolean connectives. And one of the possible solutions is mapping x, y, w to true and mapping z to false. If you substitute these things, you'll see that all the conjuncts simplify to true. And that's why the conjunction of all the things simplify to true as well. This is an old problem, which is 60 years old, pretty much. Well, since then, we only know that this is pretty complex. And DPLL, well, with possible many heuristics improving that, it's still the worst case scenario requires us to enumerate all possible SAT assignments before finding one or proving that's unsatisfiable. However, different state-of-the-art tools, they really scale to instances with millions of variables, and that's why they can solve Boolean formulas that arise from many verification tasks of real software. SMT, satisfiability modular theory, is one level on top of SAT. We are again interested in figuring out the satisfiability of Boolean formulas, but the ingredients, not only Booleans, but also theory literals involving integers, reals, comparison operators, equality, arrays, floats, and so on. So basically, this theory stands for the constraint that imposed on syntax of the formula under which we want to prove the satisfiability of certain instances. So, and definitely the syntax can be pretty rich. And for each of this extension of the syntax, there exists a special decision procedure that can be useful for certain verification tasks. For instance, if you have programs with functions, oftentimes it's actually good to use uninterpreted functions, saying that, okay, I don't care what's going on in some piece of the code. I only care that if two times the same function is called, then and given the same input to this function, the outputs will be the same. Yeah, it's a very coarse abstractional, but sometimes it works. Similarly, for real or integer arithmetic, depending on what is your application, if your program uses reals, you pick the theory of real arithmetic. If it's integers, then integers. If you use arrays, then there's a special syntax for storing an element in an array and reading an element from the array and so on. If you care about bit precise and modular arithmetic, there are definitely theory for bit precise theory. Floating points, it's one of the newest, I guess, and probably the least mature theories, but still rising, getting some more popularity. So solving of SMT is based on solving on SAT to some extent, but oftentimes this theory reasoning is separating from the Boolean reasoning, and this theory solver and SAT solver, they interact in so-called DPLLT approaches. I'm not going to tell about how we solve SMT or how we solve SAT. I just assume there exist procedures that know how to do it in the best possible way. Yeah, idealistic world. I hope it be done at this point. It was the only background I wanted to make, and that should allow us to jump to actually define what is constraint horn clauses, CHC. Knowing what is SMT, CHC is just one layer on top of SMT. We still deal with formulas, with Boolean connectives, with theory, and uninterpreted functions. So CHC is a formula that has this particular form. Something implies something. And the left-hand side of that formula is a conjunction which uses formulas phi in a constraint language or adhering the rules of the theory that we picked, and a set of uninterpreted predicates, P1, Pk. And the right-hand side H is just a wildcard that may be instantiated by an application of a single uninterpreted predicate among P1, Pk, or constant false. So, and you can think about these uninterpreted predicates P1, Pk as placeholders. So a system of constraints. You can have a constraint on something. You can have a constraint on something else. Conjunction of this constraint means all of them should hold. And this implication just means that we can have constraints, the upper bounds or lower bounds, or assumptions and guarantees. If assuming something holds, then something else should hold. Definitely, this is a single CHC that describes only one aspect of the constraints. In reality, we are interested in solving systems of constraint horn clauses, having multiple these implications and multiple symbols P1, Pk, and a solution for a system of CHC is actually an interpretation for each of these placeholder variables P1, Pk, making each of this implication valid. So basically, I'll have a concrete example in a minute, but intuitively it's this, okay, it's a synthesis problem. We have a lot of unknowns, and the goal is to find this interpretation of this knowns such that all these constraints hold. There are multiple works already dedicated to this area. I'm not going to tell about this related work. Of course, it's only for your reference, because you can look at different papers already published. I'm going to tell about the approach that I developed in my research lab and collaboration, including actually collaboration with some of you in TCS. So the rest of the talk, I will give a very brief overview of several of my papers co-authored by me. So beginning with the very first paper on free corn as a solver for CHCs. Then I will show how it can be used in order to solve quantified invariants that are really needed for arrays. Then I'll jump to a more recent work on combining recursion and quantifiers for relational verification. That is really important when you want to reason in terms of pairs of programs. One program is arrays, another is ADT, that uses the approach from actually theorem proving that I'll briefly introduce as well. And I'll finish with an overview of a recent work from PLDI this year on specification synthesis that again uses constraint horn clauses. All of that is built under the same umbrella of the tool chain called Freecorn framework. Freecorn is extensible framework, open source framework, and you're all welcome to actually go there. It's been constantly improving, and I have students working on right now. And actually, while I'm giving this talk on my own this exact machine, I'm running some set of new experiments that test new feature of Freecorn. So it's a constant improvement here.
So,
Okay,
Grigory,
so
there are some questions on the chat. Is this a good time to?
yes,
So,
sure.
Subodh, if you had a question, please go ahead. Yeah.
I actually don't see any questions in the chat.
No, I don't. This is by mistake. I raised my hand. Sorry.
Okay, sure, sure. So, yeah, if anybody has any questions, please feel free to just, unmute and ask. Go ahead and ask.
Yeah, definitely. All right, so this is an example of a CHC encoding of a simple program in C. Well, you can guess what this program is doing. It has a set of non-deterministically picked integer variables. There's an array that has, again, non-deterministically picked elements and the counter I, which begins at 0 and increments in each iteration. So it's growing. So something is going on here. Basically, some variable m is compared against AI and reassigned in case if it's smaller than that. This is the verification condition that we actually really want to either prove or falsify, saying that if you pick a random j in a range from 0 to n, then aj should be less or equal than m. Okay, so m is greater or equal than all elements of array. So it may you may think about it, m is maximal, but actually m is not maximal because m is initially picked non-deterministically, so it can be picked a very large m that is always already greater or equal than all elements. So that's even simpler task, not even maximal. So in order to encode it to CHC, well, what is CHC intuitively? CHC is a logic representation of all possible behaviors of that program, including as many iterations as possible, including as many arrays as possible, and so on. So definitely, in order to capture that, we need to allow some kind of repetition. And the easiest way how to think about encoding is basically like visually break this program into three parts. One part is before the loop, one part is actually the loop with as many iterations as possible, and the last part is our assumption and assertion. So each of these actual ingredients are loop-free programs. So that can be created, that can be encoded using symbolic execution or static single assignment transformation that is typical for compilers. Well, there's a question. Are you saying that the last assertion in the example holds, but would it hold if n less than 0? Well, if n is less than 0, then this assumption becomes false because j can be at the same time greater or equal than 0 and less than 0. Then from false, everything holds. Okay, so in order to encode this program into CHCs, well, we first need to break it into three parts and consider each loop-free fragment in isolation. So we know how to deal. Well, there's a bounded model checking, very popular technique right now that can do that for us without actually need to unroll any loops, but just assuming, okay, we have a single loop iteration, it takes arbitrary I at the beginning and arbitrary M, and just if you encode that into a formula, then it will work. So the first part is just the only meaningful formula that can be used as only the initial value of counter. So here, there's a loop guard, there's a reassignment to M where we use primed variables as next state to represent next state values of all variables M prime, I prime here. And the actual verification condition, which says, okay, we have to exit from the loop. I should be greater or equal than N. And at the same time, J should be between 0 and N. And well, this is a typical thing which you do in bounding model checking as well. You negate the assertion because you want to write, if it's possible ever, to find the loop. So M greater or equal than AJ, so it's negated. So after we encoded each of these blocks individually, we need to bind them somehow. And this is where uninterpreted predicates come into play. So we introduce one predicate for each loop, and we move it, and we call it in either right-hand side of each reduplication or left-hand side or both. So that intuitively means that if we begin in this state where I is equals 0, then we go to the step where we can actually go into the loop. Here, if we begin in a state where something INV holds and this conditional fulfilled, then we may go to the next iteration of the loop. So this is INV in the left-hand side and the right-hand side of the implication as well. And lastly, if we begin in a state where INV holds and this guy holds as well, I mean, we exited the loop, then it should be impossible that the negation of the assertion holds. So if it's not impossible and this implication doesn't work, then they should find the bug. So again, the key insight here is these are interpreted predicates, which stands for a loop head, and encoding this program in a way that capture many possible iterations of the system, which is not statically defined. So why is J not in the invariant? That's a good question, because J, yeah, it can be in the invariant as well. So, but it can be really not an invariant, depending on where we declare J. If we declare it here, then it will not be in the invariant. And the technique that I'm proposing right now doesn't actually depend on that. So we can move the declaration of J all the way to the last block. Then the while loop will not be aware of the existence of J, and we cannot use J for the invariant. And the technique I'm going to present actually, it indeed is not sensible to that. But you're right. In principle, in this particular scenario, we can make it available for INV. So once again, so the CHCs, they can stand for verification conditions, and this is the compact representation where init, tr, and wet, they express some fully interpreted information about our program. INV represent unknowns, and we can create as many finite traces by unrolling this system of CHCs. Unrolling is pretty much similar to bounding model check, as I mentioned already. So when basically we have to take this TR, we can conjoin it many times. We can refresh variables such that the destination variable here is the same as source variable here. And this is called unrolling, and satisfiability of this formula that is being sent to the SATA or SMT solver guarantees existence of a bug. And unsatisfiability means not existing, that bug does not exist for this particular unrolling. Obviously, in order to prove the absence of bugs, we need to consider all possible unrollings and prove that with formulas are unsatisfiable. Definitely, it will not scale, and that's why bounding model checker do not scale in general when it comes to large unrollings. So we need inductive invariants to prove that there are no bugs in these programs. And this inductive invariants, they are actually represented by solutions to CHC problems and the actual predicates that can be instantiated in each of these implications, making all of them true. Okay, so what is inductive invariant? This is okay, sorry, there's another question. How do you determine the K? Okay, so for bounded model checking, there's no way to determine K. There's only, you can enumerate all Ks from 0 to 1 to infinity. So that's why it will not scale. Sometimes UK can be found statically in certain cases where, for instance, you hard code number of iterations, but in general, it's impossible. And we don't do that. I'm showing this slide for reference to show a connection of CHC and BMC. So you can basically extract counter examples. In this case, you can search for counter examples for different K. But that's not what I'm going to show you. I'm going to show you the opposite alternative scenario where you search for inductive invariance instead. So inductive invariant, intuitively, it's a formula that describes all initial state that is closed under transition relation, which means if you begin in a state which is satisfied by the invariant, then we should end in the state that is also satisfied by the invariant. And lastly, invariant should exclude the bad state. So in this particular example for arrays, invariant is this a little bit crazy formula that uses universal quantifier. So it says that for all j, if j is between 0 and I, excluding I, then m is greater or equal than aj. And this is the CHC that we constructed in the previous slide. So how we can actually prove that this is indeed a good invariant? We can substitute it. So we can move this invariant here to this INV, to this INV, to this and this. And instead of CHC that uses uninterpreted predicates, we get just implications which are fully interpreted that can be sent to an SMT solver, and the SMT solver can say that they are valid or not valid. So for finding interpretation, we come to the problem of checking just if the user defined or somehow automatically guessed interpretation for NV indeed holds. And the power of SMT solve come in handy at this point, because the more powerful solve, the more such invariants we can check. So the approach that I initially published with my co-authors, FMCAT 2017, it's called Freecorn, and it's a very super high level architecture picture of that looks like you see in this slide. So there's a set of possible candidates that are captured in some grammar, and we have a standalone SMT solver that can receive any questions regarding satisfiability and can do this SMT checks, and it can return to the grammar if needed. But if for some candidate its own sequence of SMT checks succeed, then it's done. Also, it has a set of lemmas and has a set of bad tries. It tries to avoid bad candidates, and it keeps the good candidates at the same time. What's important here is that invariants are always complex. Also, not always, but often complex. In order to find a good invariant, we actually need to find good helper lemmas and then conjoin them together. So that's why this box, this storage of lemmas is here, because lemmas help to find invariant, and then also lemmas help to prove that all necessary ingredients of your invariant are there. And at the end, we just conjoin a set of lemmas, and that will become our invariant. So this is sometimes called syntax-guided synthesis, because the way how we can describe a set of possible candidates is just by giving formal context-free grammar. And then the sampling process, which simply applies the productions on the grammar and figures out, okay, this is my new candidate, and I'll proceed with that. So if it's, you probably noticed that invariant for the previous, for our example question is rather complex and has a quantifier inside. That is not really usual, because if you don't have arrays, for instance, if you have only arithmetic programs, then, well, you don't really need to have any quantifiers, because oftentimes, many times, you just need to know, you just need to prove some properties like something is positive, something is equal something, and so on and so forth. For arrays, this picture is a lot more complicated, because we need to reason in terms of ranges of values. For instance, this particular invariant tells us that for all j's, the whole sub-range of the array, something holds for each element of them. And this is a dynamic range, because it's bound by 0 from one and by I from the other hand. So basically, as more we go from as more we move, the more iterations you go, the more I grows, and that intuitively corresponds to the growing range of elements about which we know something. So more precisely, like Kafna 2019, these my great collaborators, we defined an algorithm that helps figuring out all this universally quantified invariants automatically. So, and very briefly and intuitively, it has three parts: the quantified variable that should be unique variable, the progress range telling that how exactly our range of elements grows, and the cell property, something that actually should hold for each element of that range. So intuitively, that is based on identifying counters. So counter is a special variable that always grows or always decreases in the loop. It should not necessarily be it should not necessarily count by one. It can count by two, by three, and so on. But they should be consistent. They should really go up or down, increment or decrement in each iteration. So definitely we can use static analysis to figure out a set of counters, maybe several counters per loop, and our tool and our approach actually finds them all. And then what it does is just a very simple trick. So instead of using the counter, it basically introduces a fresh universally quantified variable, and then it compiles this progress range by, again, some very lightweight analysis of how this counter evolves. What is the initial value of that counter, and what's the terminal state of the counter, and so on. And it always has the form of some counter is greater something than and smaller, less than something else. So figuring out the strangeness is relatively easy, but figuring out the cell properties is more difficult. But clearly, if we reduce the problem to only figuring out what is a cell property in this case, it's still a lot simpler task than figuring out the whole thing at once. And that's why the main contribution in the paper and main feature of the tool that you can find open source is that actual reduction of generation of different things that can be that can hold for each individual elements, and then generalizing them to be quantified over the whole ranges. Okay, so at this point, I want to stop talking about quantified invariants, and I want to switch gears to another applications of CHCs, which is sometimes called relational verification.
Gregory, I have a question.
Okay.
So, so is there a particular shape for this progress range which is coming from your grammar?
Yeah, there's
that you impose?
right. There's a the range is not coming from my grammar. Range is coming elsewhere. I use the grammar only for cell properties. It's just because to reduce the complexity of the sampling process, for enumeration process. I don't, because ranges can often be pre-computed. So I pre-computed once. I have a template for that. I don't have it here, but it basically represents the subset of array of elements. That's very intuitively, depending on where the counter begins and where the counter ends, by analyzing the assignments to the variable, analyzing the terminal conditions for loops. So I compile that at once, and then I use it for all.
And for the cell property, do you have some bound on variables? I mean, or your variable set could be really, really large. Thank you.
Variable, I mean,
the vars set.
Variables, large set.
The vars set that you have
vars
shown?
set. No, those are variables from programs. So the finite set of variables that basically, if you remember that how CHC looks like, it has certain variables that comes from program that we encode as well. Then usually not large.
Thank you.
Okay, so next application, relational verification. I don't have a lot of time, so I'll try to go quickly to cover many things. But this next two topics will be, I'll have, I guess, 10 minutes each. So I'll try to cover at least intuitively the idea. So what is relational? Okay, there's another question. Can your restriction handle invariants for search programs like binary search? Sure. Oh, binary search. Um, Actually, no. Unfortunately, for binary search, it would not work. Yeah, because there's no actual counter kind of go back and forth all the time. Yeah, this is a restriction. Okay, finally, relational verification. So what is this? We have not a single program, but have several programs, right? And we want to find how they relate to each other. So that's very intuitively what it means. And typically we have several programs and we combine them into a single one, then we have several loops as well. And if we have several loops, then we need to have several invariants. The truth is that if oftentimes, even if your invariant has form, or if in your computation has some only integer arithmetic or some particular theory, it doesn't necessarily mean that invariant that is needed for proving relational rectification that is also linear. A classic example is, representing a loop that has a multiplication, but doing it by addition. So at the end, invariant is a multiplication, variable and variable. It's non-linear arithmetic, but the computation loop is linear. So the solutions are not expressible in the constraint language. Don't follow the rules of that theory that we picked. And this is the problem. This is why we cannot really use the existing techniques to prove things about multiple programs. So transformations come to help, and the idea is, okay, if you can merge two programs into one, trying to see, okay, if one program has a loop and another program also has a loop, maybe we can merge them, and a single loop would do both things, and then we can derive a single invariant for both loops that describes how variables in one loop refer to variables in another loop. So it can be done directly at the level of CHCs, having two CHC encodings, and we can merge them into a single product CHC and solve that. It has many applications in security, equivalence checking, program synthesis as well. So I'm going to give you an idea about how we recently used this technique in order to prove equivalence between programs using arrays and algebraic data types. So arrays, about arrays, you already heard.
Hi, Grigory.
Yes?
Sorry to interrupt you. I have a question on the previous slide. So, I mean, I understand that CHC has many applications like the ones that you explained, but I was wondering, I mean, are CHCs, aren't CHCs more powerful than what these problems require? For example, they basically allow more kind of more free form syntax than what just invariant inference requires. Is that correct understanding? In other words, and in the previous solution that you suggested could have been solved easier if it was just done as an invariant inference problem versus as a CHC problem?
CHC is another representation of invariance in this problem. So it's the same problem.
It's the same problem. Okay.
Yes, it's just represented at the level of CHC, the level of logical formulas and inference of interpretations for interpreted predicates. CHC is directly built on top of SMT solver. So it allows you to pick one particular theory, for instance. It allows you to directly use the power of SMT solvers. So, and it's not related to programs. So particular program, language agnostic. So classic invariance in the generation techniques, they typically built for a language, for some language. Variant generation for C, variant generation for Java, and so on. You can take an encoder from C or Java to CHCs, and then you build the same tool, the same invariant, the same CHC solver that would discover invariants for C and Java at the same time.
Sure. So, I mean, to understand, to paraphrase you, you're saying that CHC is giving no extra power. I mean, any formula that can be expressed as a CHC can also be expressed as an invariant inference.
Well, computationally, it's the same complexity still. Computationally, it's the same challenging problem.
Yeah, I mean, one is computational complexity, theoretically speaking. One is kind of practically speaking, because I mean, it seems to me that CHC is more free form because it allows anything on the right hand side and anything on the left hand side, whereas
Well,
an
not
invariant.
really anything. Not really anything. You have restrictions of what can be in the left hand side and what can be in the right hand side.
Okay.
So it's just, but it's a matter how you encode your problem. So if you have a program in some language, so it may have, certain syntactic restrictions. It depends on you may encode it in multiple possible ways to CHCs, and then it's a matter of what your algorithm support or your tool support. And you may play with the CHC. You can use, well, in relational verification, for instance, you can transform them, and you can derive, you can pose a new question into CHC solver that would not be possible to that. In this case, yeah, it's more powerful for relational verification because it allows you to find invariants that do not exist even at the level of programs, because it requires transformation.
Okay. Okay. Thanks for your answer.
There's another question. Can your restriction handle invariants for search? Okay, your language doesn't allow multiple interpreters. No, it does. Oh yeah, it does allow. Yeah. So I don't understand why you can't. We can. The point is that we rely on SMT solvers, and SMT solvers, T in SMT means theory. In theory, it needs to be defined in advance. So if T is your linear integer arithmetic, that it cannot work for nonlinear integer arithmetic. That's what I mean by inexpressible. So, but if you somehow figure out that you need nonlinear arithmetic for problems that use only linear arithmetic, why not? You can actually. That's the point, but it would require you a lot more resources. The complexity will be a lot higher, and well, you need to decide that you need to go for nonlinear. Yeah, so someone has to come and tell, okay, I need linear CHCs, but nonlinear solutions. Someone has to make this decision. But if we do transformation, we don't need to think about all of that. So for arrays and ADTs, yeah, so why it's actually important? Because, well, you may have specifications that uses ADTs, algebraic data types, and you may have implementation that uses arrays. And you may have the same data stored as array on the same data stored as ADT, as a linked list. And, well, how do you end up with proving that they are equivalent or not? So a particular example here is implementation of a stack in Python or Python looking language. So the one is uses lists and another uses arrays. So this is kind of an object that the class that uses, pair by pair, the same operators you read in a different language. So we can initialize the array, we can push and pop, and you can see how different operators look and using different data structures. So and observational equivalence said, okay, no matter which inputs we give to these implementations, the outputs, whenever we come to actually getting outputs from these classes, they should be the same as well. So basically, content of arrays, content of stacks should be the same. So, and it may be difficult to see for the first time, but actual invariant that can describe that observational equivalence looks in this way. So it's a recursive predicate. So, and it tells us approximately that if your stack is empty, the list implementation, then your counter in the array is 0. And if your stack is not empty, so it's created by consing another stack and variable y, then first of all, the counter is greater than 0. So there's something in the array that actually represents data in your data structure. And this equivalence of these cells versus the content of array and content of stack is represented by this equality. So that variable y that sits in the head of the current list can be found in your array using that some particular value on the counter. Yeah, that tells that equivalence of a certain two elements. And this recursive call tells that we have to repeat this for a reduced range of elements in an array and a reduced list until we find an empty list. Yeah, so again, that looks like complicated, and it's recursive predicate. And yes, inductive invariants can be recursive functions. And our goal and the point of that paper that appeared TACAS this year is how to automatically synthesize these recursive predicates. So we definitely need a template for that. And the template goes approximately like this. So we admit, okay, we need a recursion. So we need to have these cases, if something is nil, if something is not nil, we need a recursive call, but we don't know what's going on in the base case, what's going on in the inductive case, and we don't know all these arguments that are useful. So if you consider a more generalized template, then we basically don't even know that we need a particular array, particular counter. Maybe we may have several counters, several arrays, and so on. So this is the actual template that we deal with. So, and we then attempt to generalize. We attempt to synthesize these placeholders and see what's going on in each of these places, in the base case and the inductive case. So what's the key idea? Very briefly. So the key idea is figure out what can be given as input, what can be received as output for some of the pairs of implementations in two programs. And well, we also need to look at if some methods in the programs require preconditions, and we need to make sure that precondition in one implies precondition in another, and vice versa. Equivalence of outputs, of course, and the progress of the data structure is the same. So if it grows here and it grows there, if it decrements here and decrements there as well. So remember, it's all represented as a big CHC that has both ADT program and array program. Recursive predicate is a solution for that CHC, and it uses recursive template. So this CHC solver goal is basically instantiate these holes in that template that you still see in the bottom of the slide, and check that it's indeed true. So how to check that I'll cover in the next slide, but the last hint, the last insight about this progress is that, well, you can think about that as a consumer operation, because basically if you take an array, you take a list, we consume it, we can see, okay, what's the content of that, what's the head, and then we recurse by looking at what's the what is stored, what is the tail of the array. So we call the separations consumers. Similarly, there are producers that grow the data structure, and no ops that return true and false, basically some things that can observe the internal state. And the algorithm that we use for the CHC solver makes use of these producers, consumers, and op operations in order to find different chunks of this invariant. What's a lot more important actually is how we can prove that given recursive invariant is actually an invariant, because it's recursion, and it needs to use some theorem provers that needs to work by induction. And by, some of you may know, there are different groups, right, in theorem proving communities, the automated SysMT solvers and proof assistants that require manual, some human interaction. And definitely there's a trade-off between automation and expressiveness. The more automated, unfortunately, the less expressive formulas we can solve, and vice versa. The more expressive reasoning we need, the less automation is needed. So I'm happy to.
Grigory, a question?
Yes.
On the previous slide, I'm just wondering why you can't phrase that as a normal CHC problem, right? I mean, you have this
It is
R.
normal CHC. It is
Okay.
normal CHC
Okay, so
problem.
there's no recursion, explicit recursion and stuff like that we need to worry about.
But the point is that you unlikely will be able to find non-recursive predicates. You may use quantifiers instead, but it's still hard. I don't actually.
Okay, so you're saying that the structure of the constraints would look something like this.
The structure of constraints will, well, I don't show it here because they're actually quite large and they won't fit even a slide. But the solution is difficult to find, because you need to reason in terms of a linked list and array at the same time. So the question is how, and you don't know what's the length of your linked list and what's the length of your array. So you need to, your invariant should express this equivalent for random ranges of elements. And that's why you either need quantifier or recursion. And we found that recursion is well suited here. Sometimes we can use quantifiers as well, but without recursion or quantifiers, I doubt it's possible.
Okay.
Why can't you use fixed point solver? Well, give me one and I will use it. There's no one available for this type of problems. Something in theory, yes. Some theories maybe, but coming to actually work in implementation, no, don't exist. Or authors hide that. We looked. This is the one of the things that I also have in the tool chain. It's called ADT and Prover. It sits right in the middle of automatic theorem provers and more traditional theorem provers. So it still uses induction, but it uses simply solvers in order to prove something useful. So this is a paper from Constraint Programming Conference 2 years ago. So, and the idea is that we have universally quantified recursive program formulas, and we want to prove them by induction. So we search for different sequences of publication, so what assumptions imply, and we backtrack if some assumption fail and so on. So sometimes we use failures to synthesize new lemmas and repeat the whole process after adding these lemmas to a set of assumptions. And it's built on top of Z3, and actually that is robust and powerful enough in order to prove formulas from the previous application where we want to prove validity of recursive formulas as solutions of CHC tasks. Okay, so I have like 5 minutes. I want to show you just a brief idea about the last application of CHC, which is also the most recent our result on specification synthesis. So look at this small program that has a loop and now a known number of iterations and assertion. So counter X is 19 in each iteration, it gets Z, which is unknown, and it should be compared against Y, and Y should be greater or equal than X. So this is assertion that should hold for any implementation, but the point is that we sometimes don't have implementations of F and G. They just don't have a source code for that we can use to encode in our CHC. So the question becomes different. So give me the most permissible implementations of F and G such that this assertion holds. So what could return and what F could do, what G could do. So one of the simplest but also useless implementation when it comes to C is just, well, F or G doesn't do anything and just exit the whole program. So in this case, assertion is not reachable at all. Yeah, because assume that exit is G. G starts and exits. Assertion is not violated and nothing bad happens. So we're good. It's not just reachable, it's trivially unreachable. And that's why it's trivially true. So definitely that's not what we actually want. We want to have some meaningful implementation such that F returns 0 all the time and G returns 19 all the time. So that just means that X counter X is the same, and the loop doesn't actually change that, and G return 19. 19 greater or equal than 19, it holds. Yeah. So if we given this particular implementation, then we're good. However, well, this is only one possible case. So if we manage to, if our implementation is somewhat more complex and F returns anything from -infinity to 0, and G returns anything greater than 19, that you will see that it will still work, because in this case, X will decrement, will get a little smaller and smaller, and Y can be larger than 19, and something that is larger than 19 will always be greater than something that is just smaller than 19. So coming to the terminology, well, we call that the simplest and useless specifications are called vacuous. Normal specifications return, let's say, simple, constant. They call non-maximal, just normal. And the most permissive, they're called, they in the best case scenario, they're called maximal. Maximal means that they cannot be extended any longer. And our goal in this research direction is to figure out the maximal specifications that you really cannot extend further. So this is what we did last this PLDI paper. We encoded into CHC system as well in exactly the same way as I showed previously. The difference is that now we have F and G, and F and G are not really known. How is exit 0 and return 0 different? Well, if you have return 0, then you reach the assertion. If you exit, you don't reach an assertion, you just exit. Health. So if you want to use CHC solvers, well, we want to use this kind of encoding, but we don't have F and G. So, and if you have F and don't have F and G, then clearly, well, no constraints over F and G. And a simple, trivial solution for this system would be, well, F is false, G is false, and I and V should be, true. Yeah, so false implies anything. False implies anything. It works, and that's vacuous and that's useless. And in fact, most of the existing CHC solver, let's say space serial direct, they would just return false solutions immediately. And that for specification synthesis, that's completely useless. For non-vacuous solutions, well, we can simply use the existing algorithm for CHC solving, but adding yet another non-vacuity check. So let's say sampling candidates, getting something that this looks good. We just check if it's useless or not, extra SMT check. And if it's useless, then we continue searching for something else. If it's not useless, yeah, we're done. And maximal solutions is extremely more challenging because we want to find a non-vacuous solution and try to see if it can be extended by at least a single model, and a single model again and again and again until we find that it cannot be extended any longer. So the big idea of this approach that is called Horn spec is that, well, we use this non-vacuity solver that gives us solutions which are meaningful but maybe not maximal. So we can use a SIGO solver for that, and we can also actually use an SMT solver for that. Apparently, SMT solvers are not that bad as, for instance, we saw it in the beginning. We also use a CHC solver that the freecorn basically built on top of freecorn that try to infer this in non-vacuous solving using mainly quantified elimination. This using backward and forward propagation. I'm not going to tell what it is, but it's essentially based on quantified elimination. And we also have a maximality checker that for each non-vacuous solution just has to confirm or not confirm that the solution which we received is good or bad. So if everything is good, we're done. If not, it's not good, then there's a loop back where we compose a new system of CHCs that needs to be solved in order to extend the current non-vacuous solution. And then we go to the maximality checker again and try to see if that works or not. So this is a very big idea, very roughly, because I'm running out of time, but more details definitely can be found in the paper. And this is I'm really excited because this is the work with 3 of you, I believe you all 3 right now listen and attending. It's a collaboration with you guys. I'm looking forward to extend that. So it's all available, it's all open source, it's all built on the umbrella of the freecorn CHC solver. So we use the recent advances in Z3. However, in principle, it can be extended to different SMT solvers. So I don't have any evaluation slide right now because it would take a lot of time to describe that. But you can look at paper, you can look at different plots, and you can actually run that. So it's pretty sure it's comparable. Spatial, Darica, Hoyce, other checkers on more than 500,000 of public benchmarks that also can be found in our home repository. So briefly, strong points of freecorn. First of all, it's support for quantifiers, support for recursive predicates over data types. So of course, because it's undecidable, then by saying it supports, then I don't want to say it's a full support. It's reasonable support. And in addition to sampling and enumeration, we also use forward-backward propagation using quantifier elimination. And lastly, of course, maximal specification synthesis, a brand new feature. And I wish to thank my collaborators from UW, from Princeton, and from TCS for helping me to helping to build all this beautiful infrastructure, which is extensible and ready for use. Okay, that pretty much concludes my talk. What I presented 3 applications of CHCs to verification of program safety, and particularly programs using arrays. A little bit about relational verification and specification synthesis as well. What I didn't cover, what I also worked at, is automatic parallelization using CHCs that helps discovering equivalent programs which are easily parallelizable, verification of security that naturally comes from relational verification, termination analysis, proving that programs terminate or never terminate, that also can be done on the top of CHC solvers. As for brief future work, well, we're currently working on quantified specification synthesis that is extremely more challenging because of quantifiers again. So you can use CHCs in order to find performance bugs as well, and also repair performance bugs, finding like something that is not really not some programs that will take a lot of resources and improve them, and definitely termination aware. How do we find something that eventually terminates as opposed to something that may loop forever? Definitely, well, in talking about synthesis, we could be interested in either of something that always terminates or something that never terminates. Could be seen as 2 different problems. Thank you for your attention. Sorry for taking a little bit longer than you expected. Thank you for questions that I already received. And well, if you have more, then definitely we can discuss, or you can reach me offline as well. Thank you.
Thank you, Grigory. Let's give you a hand for that. Thank you. So if anybody has any questions, please go ahead and ask.
Yeah, I have a couple of questions on the specification synthesis work. One is when you say maximality, is it with respect to some grammar, or the second related question is, what kind of theories are you working on? Are you working on linear integer arithmetic, bit vector arithmetic, or something else? Or does it not matter? And third, I mean, so you showed us an example of maximality where the specification was synthesized for this example, motivating example that you used. But could you also share some, some more interesting kind of examples where this kind of thing was really helpful? Yeah.
Okay, yeah. About regarding maximality, we don't actually, yeah, so there's no grammar restriction. So the maximality checker works like posing quantified formulas to solver, and it's intuitively that says, okay, I'm currently considering this predicate. Is it possible in principle to extend it by at least a single model? So that's the question we ask the SMT solver. And if SMT solver tells us, yes, it's possible, then we go and extend. We may use some helper grammars for each of these individual steps, but eventually, well, when we guarantee that something is maximal, that's like absolutely grammar agnostic decision, because it's actually several loops, and it keeps looping for as many times as actually needed to actually prove maximality for all possible things. So
I mean, the
yeah,
loop would go on forever, right? I mean, because I mean, unless you kind of, I mean, what's the termination guarantee here, right? I mean,
it's all undecidable problem. Of course, it's all these loops, everything. This guy can go forever. This guy can go forever. This guy can go forever. It's all hard problems. So there are no termination guarantees in general. For some particular cases, for finite state, for finite state systems, perhaps for bit vectors, maybe there could be guarantees for some fragments. But those are special cases. In general, of course, there's no guarantee. So your second question was about theories. Well, this currently works for linear integer arithmetic, and as I mentioned, we currently extending it to non-linear to arrays and quantified reasoning. So it's a work in progress. There's something else already works, but it's hard. It's too early to basically present that.
Does it matter whether it's bit vectors versus integers? I mean, is it even?
It
You mentioned arrays,
matters
but
because
bit vector, yeah.
bit vectors matters a lot because the CHC solver that we actually use here. So as you can see, I didn't explain what is backward and forward propagation, but essentially it's a quantify elimination. So intuitively, that means, okay, I'm beginning my init state. Now I'm going to the loop, and quantify elimination helps me to understand how my candidate will look next iteration. So I'm sort of doing some, it's some kind of a strongest post condition inference and I'm using quantify elimination for that. For integer arithmetic, even for arrays to some degree, this isn't doable and not extremely difficult sometimes, for some arrays. Just don't want to say that for all the arrays. But for bit vectors, it's a lot more difficult because then it becomes a lot more complex. And existing solvers and existing quantified elimination algorithms for bit vectors, they essentially boil down to propositional level, to bit blasting, and to QBF at the end. And this is extremely not scalable, and it could be a lot of problems and issues, like performance issues with that respect, but in principle doable. So you also asked about big examples. Well, I don't have them right now, but you can find examples in our open source repository. We take examples from competition for constraint horn clauses that I have uh, I have pleasure to co-organize as well. Doesn't mean that I'm biased. It just means that I have a call for benchmarks, and many people who work on the CHC level, they send me this, send us, not only me, the benchmarks. Then we group them category per category, depending on what kind of features they have, these benchmarks, what kind of common characteristics. So then it's they're also available, and we took some of that, some of the categories, which is not the simplest one, but which requires functions, which requires multiple loops. Some of them even have mutual loops, like F calls G and G calls F, mutual recursion. So this is where we take, I believe they're interesting because, well, they're standard in some extent, and they're still challenging to some extent because tools compete on them. And if you look at reports all available about the recent competitions, you will see that pretty much any track in the CHC competition has problems that no one else can solve. No one can solve at all. Yeah, so I hope I answered, at least covered some of your questions. If I forget something, please remind me.
Yeah, thank you. Yeah, thanks, Gregory.
Does this present approach of invariant generation cover loops with multiple termination conditions, for example, loops with multiple break statements and branches of if statements? That's okay. Nice question. We believe, well, the beauty of CHC is that we take care of all these termination conditions at the level of encoding. So we look at all what happens, all possible things that can break the loop, and we apply certain transformations, the semantically preserving transformations at the beginning, at the encoding level, where all these break conditions moved to loop heads. And loop heads become complex. If we iterate until something else, or something else, or something, and at the end, this becomes our loop guard. So And at the CHC level, we don't really care already at this point because that's already done at the previous level. And it does not affect the does not semantically affect the invariant that you want to generate, because you're still looping and you're still finding some property that holds in each iteration. You mentioned symbolic execution. Is it used in CHC translation? It's used at the translation step by verification front ends. Let's say if you know what CBMC is doing, that's pretty much similar. CBMC, for instance, first uses go-to-CC representation, which is actually symbolic execution, and it presents SSA form, the go-to-CC level, go-to level. Then it flattens the formula to a SAT formula, and it employs an SMT solver, a SAT or SMT solver for that on that formulas. And CHC we do similar things. So we rely on external tools that would run the similar processing on the level of initial programs and generate, but don't generate go-to-CC, but generate CHC. And then the CHC go to CHC solver as opposed to SAT or SMT solver. So the flow is very similar, and the ingredients are slightly different. Okay, any other questions?
So, Grigory, I had a question. When you, I mean, do we really make use of the fact that these constraint horn clauses have this, horn structure, conjunction of things on the left and just basically one negated kind of clause, literal in the clause? I mean, is that used crucially in your CHC solving? I mean, you didn't speak much about that, but
It's well, that's a good philosophical question. So first of all, I don't see where this, if you just allow for arbitrary, arbitrary formula on the left hand side, if you just like disjunctions there, for instance, I don't really see where it can immediately be useful. And because well, if you use program with functions, say we call this function, we call that function, we call it third function, all of them should fork, and all of them should work, means we can join them. So disjunction would mean something like we either call that or call that or another one. But if it's a disjunction, we can split this CHC, which has disjunction, into CHCs, because with this verification, there's nothing like either that hold or another thing hold. So we need to exploit all possibilities, and that's why we should have two different CHCs for that. And and we still end up with this syntactic restriction. So in this case, technical. Well, if you have the second aspect about how if it's useful when solving, if we have a synthesis tool that based on syntax guided synthesis, then actually, and based on numeration, then really, well, this particularly you can work with any kind of type of constraints, with junctions, with head. In a head you may have also conjunction of things and disjunction of things, or a mix of things as well, because it's a thing. It's enumerate and try. Enumerate and try doesn't really, yeah. But in freecorn we don't just blindly follow this enumeration strategy. We have heuristics that improve the process, improve the performance by exploiting different facts about the structure. So, for instance, the backward propagation. If we begin in a property that we want to prove and go step back and do this weakest precondition. So, if we have a disjunction there, well, we would find weakest precondition for the disjunction of things and what to do with that. If we have a conjunctions, then we have abduction and multi-abduction, and we can split, we find stronger effects, and then we can use these strong effects in order to proceed, move on. But if it's disjunction, I don't know what to do. So many, and if you look at PDR on all other things, then they really build under assumptions that you need to have this conjunction. So they need to, they are more sensitive, of course. The more you go for more traditional approaches, then they're more sensitive. We have some kind of a hybrid integration. Well, in some cases we are okay, but some other cases our heuristics won't work. How about for concurrency and non-determinism? How well does it fit into CHC format? Okay, non-determinism you saw, because we had non-determinism, non-deterministic assignments. It just non-deterministic means we don't have constraint. So if you have a counter that it begins with 0, then we have variable equals 0 in our constraint. If we have non-deterministic assignment, then it's just true. We don't have anything. Concurrency can be encoded. I think there's a rely guarantee approaches. I think Deepak has a paper on that. I'm not working on that personally. Freecorn doesn't support that, but I believe if you can encode concurrency into just CHC, then we can still use existing CHC solvers and to solve these problems. Well, Deepak, correct me if I'm wrong.
Yeah, I mean, that's more or less accurate. I think I have a slightly different view of the CHC. I mean, I view it as capturing a proof, about a program. For example, if it's a sequential program, you're proving that some assertion holds, right? So it's maybe capturing a Floyd-Ho style proof of that the program satisfies
Right.
that property. Similarly, you can, as you said, you can
yeah.
have rely guarantee or Wikigrees kind of proofs for concurrent programs. And once again, those also form, I mean, they fit into the CHC kind of constraints. So, I mean, if you're, as long as your proof style, your proof, your proof, the way, I mean, your proof, the notion of a proof of your program satisfying the property, as long as that can be captured as a CHC, then yeah. So yeah, it's a fairly general. I mean, I don't know any proof system which is not, captured by a CHC as yet. I mean, at least the popular ones are.
That's I totally agree with that. So. Okay. What is the number of typical guesses that need to be done in a typical invariant search? It highly depends on which heuristics we use. Initially, Freecorn was the first iteration, the first increment, the first, I would say, beta version of Freecorn from 2017. It was like a naive invariant and naive enumeration. And for even simple programs, we saw cases like 10,000 of guesses, and which required, but each of them were pretty fast, and like 10,000 of guesses, maybe like 5 minutes or so. Well, it's not extremely fast, but still not extremely long time, long processing. After improving the heuristics on top of heuristics, we were able to see that not only the number of guesses decreases, but oftentimes the whole need for doing the guessing disappears, because you do more inference as opposed to search. You do more forward, backward propagation that oftentimes you don't really need to solve to enumerate from the grammar if you able to get useful fact from just weakest precondition and strongest postcondition style inference. So right now, Freecorn is like a crazy combination of different techniques that all try to, it looks like a portfolio, maybe if you wish, but which tries to try things that often works on majority of cases. Then if it doesn't work, then try something else and something else, and doing the sampling as a last resort. So, and then definitely, yeah, if we see that the cases, if none of the heuristics actually work, then it may go forever, really, like thousands or tens thousands of tries. It's an undecidable problem, so there's no limit in general. But you're talking about asking about typical, yeah, typical benchmark. Well, it's typically it terminates even before sampling. So that's typical instance. Typically, we already covered it by some other heuristic.
Okay, Gregory, I think we should wind up now. So thank you all for participating, and thanks very much to Gregory for an excellent, enlightening talk. And
Yes,
yeah,
I'm looking for collaboration,
yeah.
and this is all open source again. Have a number of possible other approaches that can build on top of Tricorn, yeah, and feel free to ping me anytime by email. So
Sure.
excited
Yeah.
about having so many questions.
Yeah. So thanks again, Gregory, and I just request everyone to unmute and just give him a hand. Okay. Thanks everyone for joining. And yeah, if you all would like to be notified about the talks in the series, please just send a mail to the email ID I put on the chat, vss.iarcs@gmail.com. And yeah, I mean, everyone from, I mean, it's not restricted to people from India, and anyone is welcome to sign up, subscribe for these. So yeah, thanks for joining. So Madhukar, you were able to join finally?
Yes, Deepak, I joined.
Okay.
I joined a little late though. I hope that didn't.
No problems.
cause
Only I
any-
asked Sumant to be a co-host. I was just worried that in case I
Okay, okay,
dropped
okay.
off, then
Yeah, I'm sorry. I could not inform in advance.
yeah, no
There's some
problem.
internet issues and I could not. Yeah.
Okay. Okay. Yeah. So I think it
So
went off
yeah,
well.
yeah. I think somebody else may be able to tell better. I joined in for a very little amount of time, but I think it did go very well. And I think there were about 50 participants, at least.
Right.
Yeah, till the end of the talk. And so next month, Deepak, on the 1st itself, we should, the 1st of September.
Okay. So do we have this?
I don't know. I'll have to ask Rahul.
Okay.
Yeah. But should we plan to have it on the 1st?
Yeah, we can do that. Yeah, I think Akshay said he would. He had some constraints about Wednesday, but we could maybe
No,
if
no.
you
I
just
think,
yeah.
yeah, I thought he had constraints about the evening because there was some Oxford seminar series which happened in the evening.
Okay.
Yeah. So the time, I think he was more concerned about.
Okay.
But so what do you think? Afternoons are better, or we'll keep it this time, or how
I
do you
think this seems to be a good
time?
time. Yeah.
So then we may want to move it from Wednesdays to.
So yeah, I mean, is his thing every Wednesday or is it only?
I
Yeah, I don't know, but I think
So
it's
maybe we can discuss that in that group. Maybe we can
yeah,
just
yeah,
also
certainly.
loop them in that.
Yeah, sure.
Okay. Okay, thanks.
Yeah, thanks a lot.
Madhusala.
Sandeep.
Okay.
Bye.
Bye.